Zohar, please.
Okay, thank you all for coming again. So I'll start by summarizing what I did yesterday, and then I'll do one more. Okay. So first of all, I discussed at the beginning just the motivation for why extended operators are important, and then I talked about what operations, what manipulations we can do with extended operators. I emphasized that we cannot do general linear combinations of extended operators. We can only do what we call direct sums, which are linear combinations with positive, non-negative integers, I mean. So this is very different from local operators. And actually there was an interesting discussion with a couple of students of how to prove that. And I don't know of a proof in Euclidean signature. As I explained yesterday, this idea comes from thinking about the Hilbert space interpretation. Then I discussed the notion of parallel fusion, where you have two impurities and you replace them by one effective impurity. That's the closest that it gets to what's called stacking. Another student asked me a very good question at some point about that. So there is a notion of stacking in topological field theories that many of you are experts on. Fusion is the closest it gets to stacking. And then the normalization of extended operators is universal. And we have 2 points of view that I always switch between according to what's more comfortable. One is you can think about extended operators as acting at some given time slice. So they're just acting on the Hilbert space. Or you can think about them as changing the Hamiltonian, changing the Hilbert space by some local degrees of freedom and some interactions of these local degrees of freedom with the path, with the rest of the system. Okay, are there any questions about this general summary? Yes?
Maybe one general thing, because we talked about it before, so do you have a physical interpretation for what adding a zero defect would mean? Because fusing with a transparent defect seems like a unit for fusion.
Right, so one special extended defect, that would actually be important when I get to the circles. So one important defect, which is just the unit operator in p dimensions. That's a p-dimensional defect. It's just the unit operator. You haven't done anything. There is no impurity, in fact. This is a unit with respect to fusion. So if you don't have a piece of garbage, then your piece of garbage fuses with it in a trivial way. It stays the same. For the addition operation, this is not a unit. So this is not a zero for the addition operation. You need a zero. When you study some defect direct sum with the unit, that's a highly non-trivial operation because you've extended the Hilbert space on the defect by one more qubit, by one more state in the vector space. Not one more qubit, by one more state in the vector space. So that's a non-trivial operation, but a trivial operation is zero. So we also have a defect that we might need to call zero for this to be the unit under addition. Zero doesn't mean much to me, so I don't know really what to say about it. It's a zero-dimensional Hilbert space on the defect. So that's the best I can say at the moment. Any other questions? Okay. So then I talked about the fact that sometimes the fusion of defects is a little bit more subtle than meets the eye. So for instance, when you fuse symmetry operators, which are special kinds of defects which are topological, you might get a phase. And this phase it has to do with projective representations of the underlying symmetry G. And I gave you one example which shows this very compactly. It's a particle moving on some circle with some potential. So you can think that the circle is maybe deformed to some kind of sausage. And there is, so for pi translations, there is a central extension, which is a minus sign. And the algebra of reflections and translations, instead of being just commuting, it's anti-commuting. And this is a purely quantum effect, that translations and reflections anti-commute instead of commuting in this problem. It cannot be seen classically. In fact, the whole Aharonov-Bohm flux concept is classically absent. So the classical theory is maybe like phi equals 0. So this is a purely quantum effect that has to do with phi equals pi. And that leads to the fact that the ground state has to be a qubit, or at least qubit. That follows from the fact that this algebra does not have one-dimensional representations because of the minus sign. Okay. Then many students asked me for more examples to learn about this phenomenon of central extensions in quantum mechanics. So I wanted to show you one more example. That example, I just called this example the Bloch sphere. I don't think it's a standard name, but I'll just explain the example. So the classical, okay, so we start with a particle that's moving on the Earth. So we just have a particle on the Earth, okay, on S2. We have a particle on S2. Let's study the particle on S2. What is the action of so e to the I action? We need to do a path integral over all the possible trajectories. That's the quantum particle on a sphere. We do a path integral over all the possible trajectories of a particle that's moving on the two-dimensional sphere. So what is the action of a particle moving on the two-dimensional sphere? It's just the kinetic energy. So let's assume that the particle has just kinetic energy. So it's dt and dot squared. I can put a half. Okay. Also. Okay. So what is the classically? It's just a particle moving on a two-dimensional sphere. There is nothing to talk about. It just moves on geodesics with some velocity. Quantum mechanically, the ground state of the system is unique. So what's the wave function of the ground state? I'm sorry, I should define what n is. N is a vector. It's a location on the sphere. So n squared is 1, and you can take n to be nx, ny, and z. It's just a vector pointing from the center of the sphere to a point on the sphere. It has unit norm, and here we take the derivative. So that's just the ordinary kinetic energy. So in the quantum system, this quantum system has a unique ground state. And what's the wave function of the sphere? Does anybody remember? What's the wave function of the sphere as a function of the theta and phi angles?
Spherical harmonics.
Spherical harmonics are, yeah, so the general solution is that wave functions are spherical harmonics. That's the general solution. And the ground state is unique. The ground state is equal to just a constant. So the ground state is just a particle that's completely smeared on the sphere homogeneously. And the ground state is SO3 invariant. It's invariant on the rotations of the sphere. So this ground state is SO3 invariant. I'll denote it like that to look fancy. Okay? The symmetries, of course, I should have said. What are the symmetries of this problem? What are the symmetries?
SO3 rotation.
Great. We have SO3 rotations. There is one more symmetry. Reflections. We have reflections. Actually, it's a direct product in this case. So the full symmetry group is O3. So that's more or less the end of the story for a particle moving on a sphere. There is no anomaly. The symmetries are realized exactly as you would expect, and the ground state is unique. Mr. Berry found, I don't know when, a very interesting modification of this theory that makes sense in quantum mechanics. It doesn't have a classical analog. So he added another term that I'll call I times Berry. Okay, now I'll describe what is this Berry. That's called the Berry phase. So what is the Berry term? So Berry described the following modification of this theory. So if you think about the path integral, let's say time was compact, so then the particle would do the history would be some closed loop on the sphere. So let's say this would be a possible contribution to the path integral, that the particle just goes around some closed loop. So Barry said that we could modify the path integral by adding a term which goes like the area of the loop divided by 2 pi. Okay, you just calculate the loop, the area of the loop, and you divide it by 2 pi. And the magic thing about this modification that Barry introduced is that it doesn't actually matter if you take the area of this loop, the complement, or the area of the smaller loop. It doesn't matter, because they differ by 4 pi squared, which is the area of the unit sphere. And 4 pi squared divided by 2 pi is 2 pi. And if you stick it into the exponent, you get 2 pi I. So that cancels out. So that's why the Barry term makes sense. And in fact, you can put any integer, k, in front of the Barry term. That still makes sense, if k is an integer. If k is not an integer, it doesn't make sense anymore.
So this is just for closed paths?
So I described how, so one very conservative point of view, sorry, who asked the question?
I didn't.
So one conservative point of view is to define the Barry term for path integrals with closed path, where time is compact. You might want to define, of course, the path integral with open time and define boundary conditions in time, define states, but that would take me more time, and I don't want to go there.
Would it be like some kind of a parallel concept?
Yeah, you'll need to define a little bit more structure to define this path integral with open boundary conditions, but I don't want to get there. Okay, so this is the Barry term, and this term has remarkable consequences in quantum mechanics, while in classical mechanics it's not even visible. In classical mechanics it's not visible because the geodesics are always of the same area. They enclose always an area of 2 pi squared, so it doesn't do anything. But in quantum mechanics, when we do a sum over all the possible histories, it modifies the answer completely. And a famous fact is that now the ground state is twofold degenerate. So you can describe the ground state as a cubic. So a general linear combination is known as the Bloch sphere. That's why I call this model the Bloch sphere. Let me just write it here. Area by 2 pi. So the ground state in this system with a Barry term is a general linear combination of 2 states. So now the ground state is twofold degenerate, and one way to parameterize the ground state is as a general linear combination of 2 states. And this theta and phi are just the coordinates on the Bloch sphere. This is not the same as the original sphere. These are just coordinates in the Hilbert space of ground states, theta and phi. And SL3 acts in a very funny way. So you can ask, how does SL3 act on the Bloch sphere? It cannot act on the Bloch sphere. Because the Bloch sphere is a two-dimensional vector space. SL3 doesn't have two-dimensional representations. Okay? So instead, SL3 acts with the following matrices. If you work it out, e to the I n dot, it's not the same. Okay. I don't want to use the same. Okay, I'll use the same n. So these are the SO3 matrices. If you want to describe a rotation by angle alpha, so how do we think about SO3? You pick a location on the sphere, and you say an SO3 element is a rotation by angle alpha around that axis. So this is how we would represent that SO3 element acting on the Bloch sphere of ground states. It's e to the I alpha n unit vector, that's the unit vector n, dotted into the Pauli matrices divided by 2. And if you work out the algebra of these matrices, there are 2 by 2 matrices. If you work out their algebra, you'll find out that they satisfy it's the same as the SL3 Lie algebra. They satisfy the SL3 relations, but there are some funny minuses. And in particular, if you take 180 degrees rotation squared, you'll get -1. So you can just take alpha to be pi, and let's say multiply as rotation around z by a rotation around z, and you'll get -1 instead of +1.
So what's the Hamiltonian for this system?
M dot squared. Well, the classical or with the Berry phase?
The quantum Hamiltonian.
With the Berry
With
phase?
the Berry phase.
You really want? Should I?
Just an idea. That's
So-
actually where you get the degeneration.
It's very similar to the particle on the ring. It has some connection A, and the connection A is some function on the sphere that satisfies this equation.
Okay, I see. Yeah.
Sorry, delta 3R. You have to. It's basically the Wu-Yang connection. You know the Wu-Yang connection?
Roughly.
Yes. So you stick the Wu-Yang connection here,
I see.
and that's the quantum Hamiltonian.
So,
Yes.
do you mean area over 2, not over 2 pi? Because area is not 4 pi.
4 pi squared. Oh my God.
No.
Oh my God. I lived too much in S3. Yes, I
So
should.
the Berry phase is a magnetic flux.
Huh?
It's a magnetic flux, no? The Berry phase.
Yeah, so how do we get this Berry phase in the laboratory? The answer is we don't, because we don't have magnetic monopoles. And you need the magnetic monopole to generate the Wu-Yang collection, but of course people invented other ways of getting the Berry phase from lots of different ways. But we cannot literally do it with a charged particle, with a magnetic monopole. I didn't say what the K dependence is. So the ground state actually depends on K. I'm just giving you the answer for K equals 1. It turns out that this funny minus sign exists only for odd K. For even K, there is no minus sign, and you get the normal representation of SL3. Otherwise, you get a projective representation of SL3. So we have an anomaly for odd K. Okay, any questions about that before I move on to the main topic of today? That was just another example I wanted to show of.
So is it because it's SU2 not SL3? So
No, the symmetry is SL3. It's just that SL3 has an anomaly. It's not correct to say that the symmetry is SU2. Hmm?
You know, it's,
Yeah, this is.
the matrix is just expression for
This is-
SU2.
Yes, this is an honest-to-God representation of SU2, but the symmetry of the system is SO3.
But
It's just that
O3
SO3
is
has an anomaly.
equivalent to
Hmm?
SU2.
Say again?
But O3 actually is equivalent to
No.
SU2.
No, they're not equivalent. SU2 is the double cover of SO3.
Yeah, but now the symmetry is O3 not SO3.
Actually, the magnetic monopole breaks the O3 to down to SO3. I think, yeah. Any last questions about this? Yeah.
So you say it's SO3 because these acts on local electrons are SO3?
Yeah, so why do I keep insisting that the symmetry is SO3? First of all, the classical problem had SO3. There is no SU2 on a particle. We live on an Earth, S2, like we are a particle in S2. There is no SU2 that acts on us. Only
How do you know
SO3.
there are not extended operators that are charged under
Right,
SO3?
so why am I insisting that the symmetry is SO3, not SU2? Because first of all, the classical model has SO3, and secondly, an interesting operator in the system is N. That's a quantum operator. And you can ask what happens when you act on it. It transforms under SO3 in the three-dimensional representation. So you get some matrix R times N. And so the local operators transform under SO3 in this system. There is no SU2. SU2 in quantum mechanics is kind of out of nowhere because there is nothing that transforms under SU2 in the real world. Local operators transform under SU3. SO3. So SU2 arises when you act on the ground states. It's an anomaly.
Okay, could I ask I'm sorry, it's a really dumb question, but I still don't understand when something is considered an anomaly, because the way I understand it is that a classical symmetry will only be a symmetry of the quantum states, that is the rays inside the Hilbert space.
Yes.
So if you want an action on the Hilbert space itself, it's natural that you'll often require cover.
So we say that there is an anomaly
Yeah,
when the action of the symmetry of the Hilbert space
right.
is a projective.
Yeah, but what I mean is, suppose you look at representations of the Lorentz group. Of course, you get a representation of SL through C, not the Lorentz group, right? In normal quantum field theory. But do we call that an anomaly?
Fermions are an anomaly, yes.
Oh, that is called an anomaly.
That's an
Okay, that's fine.
That's how we get fermions.
That's fine.
Yeah.
I just didn't.
Every time that the classical symmetry deviates from the action on the space of states,
Right.
we say it's a 't Hooft anomaly.
But I would slightly, terminologically, I object a little bit because the space of states are the rays inside.
Yes, but the action on the space of rays, here I chose a gauge. This is a famous gauge to gauge the way the rays. This is called the Bloch gauge.
Sure.
Because you see, I took theta over 2.
Sure.
So I already got rid of that freedom by removing that acts on the states with a ray. I already took representatives of the space of rays.
Yeah, so you're pointing to the fact that you can't get good representation.
You cannot get a good representation.
That I understand, but nonetheless, now if you would look at the symmetry acting on the space of rays of this Hilbert space, it would still be associated.
No.
Why not?
On this, well, if you
signs
mod
will
by
go.
phases, yes, of
All
course.
the signs will go away.
So the projective representations of a group are labeled by this. I assume you're a mathematician, right?
Sure.
So projective representations of a group are labeled by this cosmology.
Yeah.
And when we have an action of a symmetry G on the space of rays, it corresponds to a cos cycle here.
Sure.
When the cos cycle is non-trivial, we say that there is an anomaly. That's the definition.
But that's only when you try to lift it to the Hilbert space itself instead of the space of rays. Right?
Correct. Indeed.
Okay, anyways, yeah, that's fine.
Exactly. You try to lift the action to the Hilbert space. And you ask what is the cos cycle corresponding to the action G.
I'm just asking, in terms of pure physical principles, why would one expect that to lift to the Hilbert space anyway, since the quantum states are rays?
We're not trying to say that an anomaly. It's not an anomaly in the linguistic sense. It's not something is bad.
Sure.
Actually, an anomaly is good because when the cos cycle is non-trivial, we can prove that the Hilbert space, that the ground state cannot be degenerate. So if you like in this system, since for odd k I can prove to you that the symmetries are anomalous, I can therefore conclude that the ground state cannot be degenerate. So we don't use it like in a bad,
Sure, no, I
as something bad happened.
Sure.
Actually, a 't Hooft anomaly is great because we can then prove something. In fact, it's very powerful because you could ask, what if I change the action? What if I started adding n dot to the 4 or whatever? I don't know. You complicate the action immensely because there is an anomaly and cos cycles are discrete. I still know that this has twofold degeneracy. I don't even need to calculate something. You see what I'm saying?
No, I understand. So as you said earlier, so even in a normal relativistic free field theory, you view the fermions as being.
Yes.
Okay, that's
Because fermions come from some SU2 that doesn't exist in the real world.
fine. That's fine.
So it's an anomaly in some sense. Yeah. Okay. Any final questions before I move on?
Just
Yes.
to make sure, before in the classical problem you had O3 and the Z2 is broken by the variable.
The Z2 is broken by the Berry phase. Yes. 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 Okay. Now moving on. I'll come back to that story tomorrow. Now I'm just moving to a new subject that's also essential for the tutorial. We have to think about what renormalization group means. What is the renormalization group for defects? So a defect, I like to think about it, as I said, you have some lattice system, maybe a quantum field theory, and there is some piece of garbage. And of course, if you look at it very close, it looks very messy. But when you do a renormalization group flow or coarse graining, maybe the garbage looks more simple at long distances or small frequencies, small momentum. Okay? So we have an RG flow from the ultraviolet to the infrared, both in the bulk and on the defect. To simplify the discussion, I'll assume that the bulk is at the fixed point of the renormalization group flow. And this will also be something that Seaway will assume in his tutorial. I'll just assume that the bulk is already at the fixed point, that let's say Frank ran some DMRG and found the fixed point, some quantum phase transition, and he just tuned the coupling constants already to a fixed point. But this, now he introduced some piece of garbage, and that may or may not be at the fixed point. So there is still a renormalization group flow on the defect, okay? So the bulk is going to be always at the fixed point from now on, just to simplify the discussion. I don't want to have to discuss an RG flow in the bulk and on the defect at the same time. So there is an RG flow on the defect. That's an RG flow on defect. And then we do some coarse graining. And there are many options for what happens to the defect at long distances. So this is what this Venn diagram is supposed to convey. I have to go over. So let me go over it carefully. The most boring case is that the piece of garbage just disappears at long distances. So if you look at the system from long wavelengths, low frequencies, there is no defect anymore. It just restored translational symmetry. The system restored its translational symmetry, and all the correlators are just oblivious to the defect. In condensed matter, that's sometimes called complete screening. Complete screening. The defect just went away. So that just means technically that the defect flows to the unit operator. You remember that I mentioned that there is a unit of multiplication somewhere here? So trivial just means that technically it just means that the RG flow, the defect ended up with a unit operator. Then there is another option which is called decoupled. So that means that the defect in the infrared decoupled from the bulk, but it's not completely trivial. It's not the unit operator. So this decoupled means that it's a direct sum of ones, maybe a finite collection of ones in a direct sum. So that could be, for instance, a qubit that decoupled from the bulk. So the defect would flow to a qubit, but then the qubit just doesn't interact with anything anymore at long distances. All the interactions decay in the long wavelength limit, and you just have a decoupled qubit. So that's the notion of decoupled. It's a direct sum of ones. Then another option, which is yet more complicated, is when the defect is a topological operator. So the system could have some higher p-form symmetry, like we discussed yesterday, and the defect piece of garbage could flow to a p-form symmetry. That's what happens in a lot of models that people are simulating recently. They add something to the Hamiltonian, and it flows to a topological line or a topological defect. Okay? And the final option, which is probably the most common, though maybe, well, as common as trivial, I guess, is that the defect has a non-trivial infrared limit, and there is a conformal defect. So the infrared could be a conformal defect. That's the most general case, at least as far as I know. This is the most general case, and that's the case I'm going to say a few words about it. Okay. So a conformal defect is when it's not topological, so it does matter where it is. You cannot just deform it freely, and it modifies the correlation functions in the bulk, the grid functions in some important way. So I'll just say a few words about what happens in that situation, and see why in the tutorial session we'll explain much more about the structure of the conformal symmetry on defects.
In which dimension are we here?
In any dimension. That's true in any dimension, what I just said.
But you could imagine that you have a two-dimensional defect and it decouples to some conformal defect.
Say again. Two-dimensional defect that does what?
So the two-dimensional defect is in the three-dimensional theory, and
yes.
Maybe in the flow it flows to a decoupled system of a two-dimensional field theory.
Yeah, so that would be like a decoupled scenario, right. But it won't be maybe the unit operator. That's why it won't be just a finite sum of unit operators. It will just be the decoupled. It will be the decoupled case, what you just said. Yeah. Okay. So a conformal defect. Let me just draw a picture. Just for concreteness, I'll discuss 2+1 dimensions with a line operator. So in space it looks like a point. So we have 2+1 dimensional space, and we have some line operator. Okay, and we assume that this line operator flows to a conformal defect. So that means that the physics of the line operator. Let me draw a straight line. So this is the defect, L. L is the notation for the defect. So if the line operator is a conformal line operator, then the physics on the line operator preserves SL2R. SL2R comes from the conformal symmetries of the line, just the conformal symmetry of the line itself, times transverse rotations. Transverse rotations, they are like SO2 in the case of 2+1 dimensional physics, just because we have transverse rotations around the line SO2. So these are the symmetries of the system. This has to be contrasted with the full conformal symmetry without a defect. So remember that without a defect, a conformal field theory, which is tuned to the fixed point in the bulk, would have a symmetry of SO3, 2, while SO2R is just SO2, 1. Sorry, SO1, 2. Okay? So we see that the conformal line defect doesn't break the full conformal symmetry. It reduces SO3, 2 to SO1, 2. So that, well, SO1, 2 times SO2. So not the full conformal symmetry is broken, and that's the saving grace of conformal defects. They preserve just enough symmetries that we can actually say something intelligent about them. Okay, so that's a conformal defect, and I'll give you now 2 examples, so that you can see when does this actually happen. I'll give you one example, which is very familiar. So example number 1. That's the simplest conformal defect that you can imagine, because you have seen it probably in 10th grade or 11th grade. So we have Maxwell theory in 3 plus 1. Here I just draw a picture in 2 plus 1. In 3 plus 1 it's all the same, except that this is replaced by SO3, and this is replaced by SO4, 2. So Maxwell theory is, I'll just write Maxwell, this is Maxwell's theory. It's a conformal theory in the bulk. So Maxwell theory is just conformal field theory in 3 plus 1 dimensions. And what is a famous defect? Who knows of one important defect in Maxwell theory? A line operator. What's a famous line operator in Maxwell theory?
A charge.
Hmm?
Charge.
Yes. Well, what's the name of that thing? Yes, the Wilson line. What does it describe physically when we orient it in the time direction? Just a nucleus. Okay, a charged particle at the origin. So if we integrate it over time. Let's say we evaluate the connection at x equals to 0, and then integrate it over time. That just describes an external charge with charge q at the origin. And this preserves SO2R times SO3, because it's a nucleus and it's rotationally invariant. And you can calculate, for instance, what does it do? Does it decouple from the bulk? First of all, you can ask, is it trivial? No. Why? Because it doesn't decouple from the bulk. So you can calculate the average electric field. If we calculate the average electric field in the presence of a line operator L, we get, of course, the famous Coulomb formula, 1 over r squared. And notice that this is it decays algebraically. And that's exactly what you need for conformal symmetry, because the scaling dimension of the electric field is 2, and the scaling dimension of 1 over distance squared is 2, so it matches up. That's the simplest example of a conformal line operator. That's just a charged impurity in Maxwell theory. That's example number 1. And I'll give you another example. Any questions about that example? Another example of a conformal line operator is in free scalar field theory in 4 dimensions again. So let's consider the free field theory of a scalar field. There is an interesting line operator which turns out to be completely conformal, which is an exponent of the integral of phi evaluated at x equals 0 t. Integrate. So that line operator turns out to be completely conformal, even though it has a continuous coupling constant. Here, there was no continuous coupling constant. Q was an integer. It's the charge of the external particle. Here, there is a continuous coupling constant, h, but it turns out to be completely conformal for any value of h. So it's like a conformal manifold, if like in the AKLT model. It's a conformal manifold of line defects, and it's conformal exactly for any h. There is no renormalization group flow. It's conformal. This is a conformal defect because phi has scaling dimension 1, and that cancels the scaling dimension of dt exactly, and there is no correction to the scaling dimensions. So for instance, you can compute the expectation value of phi away from the defect, and it would scale exactly as you'd expect. Let me just get the refactors straight. So that scales like some coefficient, I'll fix it a little later, divided by R. This is R squared, of course. And it's exactly consistent with conformal symmetry because phi has scaling dimension 1. Okay, so these are two examples of conformal defects, but not any construction like that would be conformal. Now I'll show you an example where there is a non-trivial renormalization group flow. Yeah.
Using the operator defect rotation, can you ask if it's informed by seeing if L as an operator is invariant under dilatation or something like that?
Yeah, you have to check that this operator L is invariant under SL2R.
Okay.
It's non-trivial. How do we actually check it in practice? We calculate correlation functions of operators away from the defect and we see if they're consistent with scaling. Any other questions?
Sorry, when you say SL2R, how does SL2R act here?
Yeah, okay. I'll answer that question here. So let's say you have R3. R3 has conformal group SO3, 2. That's all the conformal symmetries of R3. If you put a line at the origin, let's say we have a line at the origin. A line at the origin could preserve a subgroup which is SO1, 2 times SO2. And they act as follows. So let's denote the coordinate on this line as t. So t goes to AT plus B divided by CT plus D, where AD minus BC is 1. So that's how it acts on the line operator. Any? Okay. Excellent. Now, one last comment about it before I discuss some general theorems. So not every line operator is conformal out of the box. Most of them, in most cases, there is a non-trivial renormalization group flow. Maybe the most famous case is the Kondo problem from condensed matter. But I'll give you a simpler example. Let's now go back to 2 plus 1 dimensions in the Ising model, the conformal Ising model. So we can write a Lagrangian, d phi squared plus phi to the 4, which is some interaction q to the fixed point. That's the action of the Ising model at the fixed point. d2x dt. So we can consider the following line operator, just trying to mimic this construction. And we just write an exponent of phi with some h. So this line operator in the 3D Ising model is not conformal. It flows to some fixed point. So there is a renormalization group flow from h equals to 0 to some h star. It's a strongly coupled, we believe that there is a strongly coupled infrared conformal field theory, and there is SL2R symmetry at long distances. What does it describe physically? So you know that there is a big discussion in the Ising model of what happens when you put uniform magnetic field, right, through the Ising system. This describes turning on a magnetic field maybe on a few lattice sites, but not everywhere. So the physical interpretation is that you turn on maybe magnetic field on a few lattice sites in some small region, but you don't turn on any magnetic field anywhere else. And the quantum field theory avatar of this problem is this line operator, because phi is the order parameter that couples to external magnetic field. So if you want to know what happens when you have an Ising critical system, but there is some magnetic field, maybe in some regions of space, you have to solve the infrared limit of this line defect. And there is a lot of measurements and simulations of this problem. This is maybe the most famous conformal line operator in 2 plus 1 dimensions. It's called the pinning field. If you search on the internet the pinning field problem, you'll find many, many papers and simulations of this problem. It's just the local response to localized magnetic field. Okay, so this is not conformal. There is some RG flow, and it's complicated.
Could I briefly return to that example again? If that's the SL2R action, then you're saying it preserves this line operator, right?
Yeah.
But the line operator is just integrating the scalar field phi along that line x
Yes,
equals 0.
yes.
Right?
It's the same here.
Yeah, but if you apply that operator, then you get singularities as a function and that kind of thing. That doesn't cause a problem.
Or singularities.
I mean, AT plus B over CT plus B will be singular at T equals minus.
This is the action of SO1, 2 times SO2 at x equals to 0. Away from x equals to 0, there is some more complicated formula.
Ah, okay.
This is how it acts on the line defect itself.
Sure.
But SO1, 2 times SO2 acts everywhere in some complicated way. And here I'm measuring, well, maybe I wasn't very explicit here. I was measuring the average value of the field at some location x and t,
Right.
away from the defect, and this is the absolute value of x. And this is measured at some location r and t. And this is the absolute value of r.
Right. I'm asking, I think, something much more elementary. Your formula for the SL2R action is AT plus B over CT plus B, right?
AB minus BC is 1, yes. Yes.
Right. So doesn't it have a singularity as CT plus D equals 0?
Oh yeah, it does.
So that doesn't cause a problem in this?
No. That's called an inversion. It's a symmetry of conformal line operators.
Okay. So this integral remains.
Yeah, it's fine. It's actually perfectly fine. You can apply an inversion to this integral. You can do this exercise, like it takes maybe a half an hour. You have to work out how the SL2R symmetry acts on phi, and you'll see that the integral is completely invariant. It's because the measure transforms by dt over 2 dt squared, this transforms by t squared, it all cancels out.
Ah, I see.
Okay, any other questions? Yes?
Maybe this doesn't make sense, but if you say that the margin from one goes to a formal different territory, can you think of this as some theory towards like doing gap?
Yeah, you could apply. This terminology, in my view, would not be precise because the bulk is gapless. We're tuning the bulk to a fixed point, to a quantum critical point. So the bulk is already gapless, it doesn't have a gap. So the line defect doesn't have its own Hamiltonian, so we cannot say if it's gapped or gapless. But colloquially, especially in the condensed matter community, when it's trivial or topological, they would say it's gapped. And when it's conformal, they would say it's gapless. But this terminology doesn't make actual mathematical sense. It's just a colloquial way of using these words. Yeah. Any other questions? Okay, so there are also non-trivial conformal line defects. And now I want to get to some theorems about what can we, like, for instance, in this problem, there is no chance that anybody in our lifetime would solve this problem exactly. We have lots of approximations for the infrared limit of localized magnetic field in the 2+1 dimensionalizing model. There's lots of measurements. We have epsilon expansion, large n. I'll quote some results very soon. But so there is no chance that anybody would actually solve it in our lifetime. But there are general theorems that do apply to this case, and I want to explain the general theorems now, and they can be tested. So now I'll get to some general theorems. So the first theorem has to do with anomalies. I'll start from it. General theorems. There will be two theorems. I'll explain two theorems today in the remaining 45 minutes. The first theorem will be about symmetries and anomalies. The first theorem would seem a little bit abstract now because it doesn't actually apply in any useful way for this example. But it would be interesting in the examples I'll give you tomorrow. So the first theorem is about symmetries and anomalies. The second theorem will be about RG flow. And that theorem is a little bit more general. Okay, so what's the first theorem? The first theorem is actually a little bit trivial. So the first theorem says a line defect is like quantum mechanics. You can think about a line defect as an interesting modification, so to speak, of quantum mechanics. line defect is essentially quantum mechanics coupled to some bath. And the bath being just the quantum critical point in which we inserted this piece of garbage. And therefore, what I told you about this, I told you about projective representation applies. So if the bath has some symmetry G, if G is a symmetry of the conformal filter in which we've embedded the line defect, if G is the symmetry, and if the symmetry is realized projectively in quantum mechanics, so if G is realized projectively on the line defect, in the same sense that we seen in the last hour and a half, then you can rule out at least one out of these 4 scenarios. You can rule out this case. So the line defect L cannot be trivial. It cannot be trivial. It can be decoupled. So the symmetry could act projectively on a sum of units, or it could be topological, or it could be conformal, but it cannot be trivial. So this theorem by itself is very trivial and silly, but it will have applications tomorrow. Are there any questions about this small lemma? It's not even a theorem, it's like a lemma. Are there any questions about it?
Yes.
Yeah.
So by that you mean that you look at the Hilbert space with one point?
Yes. You put the defect along the time direction, you have a new Hilbert space, and you act on that Hilbert space with G.
Okay.
And G acts non-projectively on the Hilbert space without the defect. With the defect, it may or may not act non-projectively. And you have to calculate that co-cycle, that phase. If the answer is that it's non-trivial, then the line defect cannot just disappear and be completely screened. It has to, at the very least, it has to be of this form. Maybe even conformal or topological.
And you consider the Hilbert space of a sphere on R2, or does it matter?
Yeah, so to be super precise, you need to put it on S2. So I'll just put it here. I didn't want to get into it, but to really apply this theorem, you have to put the defect, you have to calculate the defect Hilbert space on S2.
So you have a 3-dimensional
You can also calculate it on R2, but just to make it super mathematically rigorous, it's best to put it on S2.
So that's a 3-dimensional theory?
Yeah, but it's applicable more generally. It actually doesn't really matter, but if you want to make a super mathematically rigorous statement, then the defect has to be on S2. Okay, now I'll explain the second theorem, which is not trivial. The first one is essentially trivial, but it's still surprisingly useful. The second one is about RG flows. So it turns out that defect renormalization group flows are irreversible. So we have this picture from the UV to the infrared. This picture that we have some RG flow on the line defect. We have a line defect L, and there is some RG flow, like in the pinning field problem. And so I'm going to explain that RG flows like that are irreversible. And in fact, there is a theorem that's even stronger than Zamolodchikov's C theorem in this case. It's stronger in the sense that you'll see in a second. So you do the following construction. So I'm just going to explain the construction of why the RG flows are irreversible. So the construction is that, first of all, you go to Euclidean signature. You go from R21 to R3 to do the calculations. So this is just for the mathematical calculations. You go to R3, and then you take the line defect and you make it into a circle of radius R. So you turn the line defect into a circle, which doesn't really make sense in Minkowski signature, but in Euclidean signature it makes sense. Then you calculate the path integral, the partition function with the line defect versus the partition function without the line defect. That's one. So you calculate the path integral with the line defect versus the path integral without a line defect, and you take the logarithm of that object. It turns out that the logarithm of that, so this is the expectation value. You can think about the numerator schematically as the expectation value of a circular line defect, while the denominator is essentially the expectation value of the unit operator. Okay, and then you take the logarithm so that you would get rid of disconnected diagrams, so to speak. The logarithm gets rid of disconnected contributions. What you find is two terms. One is a scheme-dependent divergence. So if two people do these computations, they will disagree on a term which is linear in R. It's completely ambiguous. It depends how you would regularize these computations. Of course, these are divergent objects in quantum field theory, so there will be some divergence. But by using locality, the divergence has to be linear in the size of the line. So it's a counter term that's linear in the size of the line, and it's like there will be some divergence with some coefficient lambda. So that's scheme dependent. And then there will be another function that we call g of r times some scale, rg scale. Let's call it m. M would be the rg scale on the line defect, and that function is universal. It turns out that it's scheme independent. So you have to get rid of a linear term, which is scheme dependent, to get a universal function, which is scheme independent. How do you do that? A nice trick is to just take the logarithm of the ratio of the partition functions and subtract r times d by dr of the same logarithm of two partition functions. You see that if I do that, this exactly gets rid of the linear term, because r times d by dr of that guy cancels with that. And this is a scheme-independent function, which is just given by a combination of g and its derivative. And this function is called the quantum entropy. It's some function of r times m, and that's called the quantum entropy of the quantum entropy of the impurity. This is the quantum entropy of impurity.
What's m in this case?
M is some scale where the RG flow is happening. So the line defect could have an RG flow, so it has its own scale. Sorry, who asked the question? So M is some, like in QCD, there is an RG scale, which is like 1 GeV, or in the spinning field problem, there is a scale which is H in the ultraviolet. So it's some scale that comes with the RG flow on the line defect. So this function, which everybody that computes this thing would agree on, hopefully, is called the quantum entropy of the impurity. Why is it called quantum entropy? It's called the quantum entropy because we're calculating a path integral where the line defect is in a circle. Now remember in your quantum mechanics, what happens in quantum mechanics when we calculate a path integral when quantum mechanics is in a circle? It counts the number of states. It's a trace of the Hamiltonian of the quantum mechanics, right? So that's an analog for line defects embedded in some non-trivial conformal field theory. It roughly calculates how many degrees of freedom the line hosts effectively, and that's why it's called an entropy. So roughly speaking, this function is the exponent of this function. The exponent of this quantum entropy is, roughly speaking, the number of degrees of freedom that are sitting on the piece of garbage. The number of effective qubits the garbage needs to be described. Yeah.
Is it obvious this is non-negative or not?
Okay, excellent. So now there are deep questions. Can you prove that this is non-negative? No. So you can prove that it's a real number. A little bit non-trivial. So for quantum mechanics, a path integral in a circle would count how many degrees of freedom the quantum mechanics has, and it's clearly positive. For a line defect that's embedded in the quantum critical system, it doesn't have to be positive. Because when you have a quantum critical system without a line defect, there are qubits everywhere, right? There are degrees of freedom everywhere, just from the bulk. When you put a piece of garbage, it could maybe push away the wave function. So the density of states could be smaller near the line defect than everywhere else. And in that case, you expect negative quantum entropy, because effectively the piece of garbage pushed away qubits. Or it could attract degrees of freedom, and then it could have its own degrees of freedom, its own qubits. And then this function would be positive. Okay, so this function doesn't have to be positive, but it has to be a real function.
Is it change of entropy?
No, It's the number of degrees of freedom at the scale R. M is a fixed scale. It's just the scale of the RG flow. That's when you go from one description to another, say. R is the typical energy scale with which you probe the piece of garbage. R inverse. So that's the number of effective degrees of freedom at that scale. So it's just terminology. I haven't proven anything. It's just, this is how we define the quantum entropy of defects. And in fact, by now, even though the calculation requires going to Euclidean signature, and you would have thought that it's unphysical, by now there are papers that measured it in quantum computers, in quantum simulators. It can be measured in some Lorentzian protocol that I don't have time to explain. This is just the easiest way to calculate it. But it can be measured in a Lorentzian fashion. So people have now actually measured this function.
Excuse me?
Yeah,
So,
for some defects. Yeah.
So in this defects, you realize that in a group of other defects which form a fusion category, this entropy might relate to the quantum dimension.
Yes, and that's an excellent point. For topological lines, such as in topological quantum field theory, we have anyons. So this exact same computation leads to what is called the logarithm of the quantum dimension, which is denoted by log d. So the logarithm of the quantum dimension of the anyon is S. It's a special case. There is a theorem about topological quantum field theories that this is non-negative. That's from the unitarity of the modular tensor category. But we see that in critical systems, it doesn't have to be non-negative. So the logarithm of the quantum dimension could be negative. For some conformal line defects, we know that it's negative. Okay. Okay, so I haven't told you why is it interesting. And it's interesting for the following fact. You can prove a property of this function, which is that S dot, where S dot is defined to be d by dr of S, is negative definite. This is why it's interesting. So as the RG flow progresses from short distances to long distances, this function only decreases. So the effective number of degrees of freedom on the impurity decreases from short to long distances. It could even be that it's positive at short distances and negative at long distances, because effectively for very low frequency modes it's repulsive, but for high frequency modes it's attractive. Okay, so this is why it's an interesting thing. This theorem is highly non-trivial. I cannot prove it here. It will take me a few hours. So a corollary of this is that when you go to infinite large R, that's the infrared. When you go to infinite small r, that's the ultraviolet. So here we have some effective number SUV. Here we have some effective number SIR. And it follows that SUV is bigger than SIR. Okay? Yes?
Good question. I mean, here you chose a circle, but you could choose an arbitrary contour and have some scale.
Yes.
Is there anything analogous? I mean,
yeah, so
monotonicity.
You could try to calculate partition functions of squares or some ellipses. You'll get some functions which are scheme independent, but we don't know if they have any nice property.
I see. So such monotonicities are only.
It's only known for circles. Maybe it's also true for other things. We only know at the moment that it's true for circles. And the fact that it has a good limit at long distances and a good limit at short distances follows from conformal invariance. If you assume that the line at long distances is conformally invariant, it follows that S has to be a constant, because in a conformally invariant theory there is no mass scale, so this has to be a constant. And that's why we know that at very large R, this function has to go to a constant, it cannot diverge. And also in the ultraviolet, we typically assume that there is some UV fixed point. Though in lattice systems that's not the case, but in quantum field theory that would be the case. So we have some pure number in the ultraviolet, pure number in the infrared, and there is a monotonic function between them. It's of course extremely analogous to the homological C theorem. Yes? Where you assume that there is a UV fixed point, infrared fixed point. It's the same setup. But yeah. And here there is a full-fledged monotonic function. Yeah. Okay. So now I'll show you some application. One-line application of this thing, and then I'll move on. So, questions? Yeah.
So you stated the theorem in the context of 2 + 1D and line defect. Do we expect any relaxation?
Okay, so the question is how general is this theorem beyond 2 + 1D and line defect? So I'll just give you quickly a summary of what's known here. So the case of line defects, so I'll call line defects p = 1. That's the dimension of the defect. For p = 1 in 1 + 1 dimensions, this result was known 30 years ago, circa 95, by Affleck and Ludwig. That's a famous theorem by Affleck-Ludwig. And it was used very extensively in condensed matter in relation to the Kondo problem. And it counts the entropy of Kondo defects. The recent work extended it to line defects in any dimension. So now we have a theorem for p = 1 in any D. Okay? And that's useful for defects in higher dimensional quantum critical points, such as this Ising tree, Maxwell theory, many others. Another result that's known is what about 2-dimensional defects? 2-dimensional defects, let's say in D = 3, in D = 2 + 1. That's also known. There is a monotonicity theorem, but it's weaker than that. So there is no known function that decreases. There is only an inequality about the endpoints. And that's the work of Andy. He might be here somewhere. Yeah.
Well, what's an
That's the work of Andy and Kristen from 2016 or 17.
Well, what's an example of a 2-dimensional defect?
Well, there are a million of examples by now in the literature. Maybe see, are you going to talk about the interface of?
Oh, no.
No.
Just
There are millions of examples.
like Ising, yes.
Yeah, you just integrate phi squared on a 2-dimensional surface. That's like changing the temperature of an Ising classical system on a subspace. Instead of changing the temperature of the system everywhere, you change the temperature only on a sublocus. That's a highly non-trivial problem. And their story applies to that. Okay. Now I'll show you. I want to make one final comment before I move to examples. What if you have a tree? We have this Venn diagram, and I want to say what happens to the function s in each of the cases in this Venn diagram. So for a trivial defect, I'll just put it here. And SUV. For a trivial defect, what is S? Can somebody quickly calculate for a trivial defect? 0. Excellent. It has no added entropy. That means that it doesn't add entropy, doesn't remove entropy from the bulk. It doesn't do anything. What if we have the defect 1 + 1 + 1 + 1 + 1? Let's say k times. Then S is log k. Excellent. If L is topological, what if L is some topological line operator? What is S? We don't know. Any positive number is allowed. Probably there is a theorem, like Vafa's theorem, that it's a rational, quantum dimension. It's an algebraic number, maybe. There is probably a theorem that it's an algebraic number, but other than that, any positive number probably is allowed. I don't know. And in the conformal case, any S that is a real number might be allowed. I don't know if there are constraints. We have examples with negative S, positive S. Okay, so this is the story. And here you see a very interesting lemma that follows immediately from this discussion. There is a very interesting lemma that just is a trivial corollary, which is that if a defect starts its life as a trivial defect, it cannot be trivial at all distances. if there is any RG flow whatsoever. So a corollary that is essentially trivial, but just needs a tiny bit of work. There's, maybe I'll just say it as one more lemma, and then the corollary would follow. There's one small lemma that you need to prove, which is that if there is any RG flow whatsoever at any point, then S dot is not just just weakly negative, it's strictly negative. So if there is RG flow anywhere at all, okay? So if there is any RG flow at all, you can prove a stronger inequality, which is that SIR is actually smaller than SUV, not just smaller or equal. There's a small lemma that follows from conformal perturbation theory. And then you can get a corollary that is kind of cute, which is that if SUV is 0, meaning that if the line defect is essentially transparent at very high frequencies, which is very common for many defects in condensed matter, including the pinning field, and there is an RG flow, and there is some RG flow, then something really remarkable follows, that for low frequencies, it cannot be transparent. It has to be a conformal defect. So it has to be, the only option is conformal. So why did I rule out all the other options? Look at this table. Trivial is S equals 0. Decoupled is a sum of ones. It's positive. Topological is positive, because in unitary modular tensor categories, that's true. And only the conformal case can host negative entropy. So you can obtain a somewhat striking result that some defects in condensed matter have to be conformal and cannot decouple at low frequencies just from that, without any work whatsoever. And that applies in the pinning field case. In the pinning field case, that's why I wrote it here. At short distances, for very high frequency modes, this H goes to 0, because this is the order parameter of the Ising model, which has scaling dimension 1/2. If you remember your conformal bootstrap results, the scaling dimension of the order parameter in the Ising model is like 0.51 something. So at very high energies, this is completely gone. That's gone. You don't see this perturbation at high energies. So H is 0 at high energies, but at low energies, it cannot be trivial. So that immediately proves that the pinning field cannot be transparent, and it's actually consistent with experiments and simulations. People by now agree that it's a non-trivial conformal line defect at long distances. Yeah?
Could you explain, I didn't understand why the topological case has to be positive.
Is what?
In the case of topological defect, that S has to be positive. Is that obvious?
For topological defect, that's the logarithm of the quantum dimension.
Well, so it could be 0
Huh?
for a group like
It is, sorry, you're complaining about that?
Yeah.
I'm sorry, it's another mathematician shot, yes. Yes, sorry. Yeah, for invertible anyons, it's vanishing. For non-invertible anyons, it's strictly positive. I'm sorry, I was slightly imprecise. And so one corollary, that if you apply that corollary for pinning fields, you obtain that the pinning field is conformal, it doesn't decouple, and indeed that's consistent with experiments. And I'll just tell you a few facts about the pinning field now that were established by computations and measurements. And that's it for today. Yes?
All of this is true for defect RG flow, right?
Yes, only defect RG flow.
Right.
I tuned the coupling constant in the bulk to a fixed point.
Okay.
You can ask, is there something interesting to be said when there is a simultaneous RG flow in the bulk and on a defect? I don't know.
Okay.
This is a famous question in the field. I don't know the answer.
And in the pinning field case, we always think of tuning the first
Yeah.
bulk and then.
Yeah, you see, I tuned the quartic interaction to the fixed point, and then I have a piece of garbage in. So, of course, in real life, you can do both. But this is a natural thing to do, because you can always just ask what are the coupling constants for which the bulk has infinite correlation length. You tune that, and then you add the defect. In a lattice system, it's actually very similar. It's very simple. You think about the model like ZZ plus X. Usually that's kind of the model that, a lattice model that gives the Ising thing. And then you add some Z at some point 0. And that's it. So you tune the couplings of ZZ and X to get a Ising 3D fixed point. And then you add Z at some point with some coefficient equal H. And you ask what happens to the infrared limit of H. So that's how you do the simulation, in principle. Okay? Yes?
If the bulk has a conformal manifold, is it known if the entropy can depend on moduli or anything like that?
But the bulk? The bulk is just tuned to a fixed point.
Yes, but it has conformal manifold.
You're asking if the bulk has a conformal manifold, can the S depend on it? The answer is yes. If there is a conformal manifold on the defect, then S cannot depend on it, because that would have contradicted the monotonicity theorem, right? It's maybe too technical to write it on the board, but that's the statement, yeah.
For the application to the opinion field, are you saying the entropy will decrease to negative value?
Negative, yes, indeed. That corollary predicts that the pinning field at the fixed point has some negative entropy.
Is that estimation of negative value?
And I'll show you what's been measured. I'll show you what's been computed and what's been measured just in 1 second. Yeah. Any last questions before I show you the data about the pinning field? Just to the point is, I just want to show you that there are non-trivial conformal operators in higher dimensional quantum field theories, such as even in the Ising model. So people know a lot about local operators in the Ising model. There's a whole community of Bootstrap that studies them. But there are also conformal line operators, preserving SL2R symmetry. And by now we have a lot of data about one of them and some general theorems that apply to it. We don't know how many more there are. We just know a few. Yeah.
So whenever you have a dimension less than 1, bulk operator, you can...
Yes, this is called the family of pinning fields.
So in 2-dimensional,
yes.
What happens to the spin operator?
Well, you can add, that's the energy operator. Not, you mean the energy operator?
Energy, the 1/8, 1/16, 1/16.
I prefer to add the energy operator because that's already interesting. That would be an exactly marginal.
That's marginal.
That's an exactly marginal defect, which was studied by Bacchus and Brunner.
Among others, yes. But what about the spin?
The spin. Spin. Did I ever
by
think
your
about
argument, it's
yeah. Well, yeah. Do I know what happens to that? I used to know. You're asking what about the spin? I feel that I knew the answer at some point, but
Is there some data by Ivan Van?
Oh yes, I know the answer. Yes, of course. The answer is that it does something very interesting. I actually have a section about it in the paper, and it just took me time to remember the answer. So we guessed the answer, but I think by now Ananda Roy simulated it. Ananda Roy and maybe Hubert Seller, and it's confirmed to be true. So you integrate the spin field on over time, and the spin field is at x equals to 0, and the Ising model is just on a line. You just think about it as a quantum crystal line. So it corresponds to an external magnetic field, which is localized, and it can be easily simulated. And it's basically the same thing. It's basically the same, you see that it's the same thing as the spinning field. What it does is that at low frequencies, it splits space into 2. So the transmission goes to 0 at low frequencies. And it's a conformal defect which is of a trivial type. It's a direct product of 2 Cardi states. And the quantum entropy is a log of a half, because that gives you 1 over square root of 2. That gives you 1 over square root of 2. So it's log of a half and it's smaller than 0. So it works perfectly. And it splits space into 2. So the transmission goes to 0 at low frequencies, but it's non-zero at generic frequencies. In fact, there is a conjecture in some paper of Ifan that a large family of pinning fields in 1 + 1 dimensions splits the space into 2. And a similar conjecture appeared by Gerard Watts. Okay, so it came back to me. That's the answer. Okay, I just wanted to show you a little bit of data about the 2 + 1 dimensional case, the pinning field. So if you look at the theory of the pinning field, you can do large N calculations or epsilon expansion calculations, if you like those kind of things. And these are the tools that we have. And I'll just quote 2 results. I'll quote 2 results, which both agree with Monte Carlo and experiments. So one is S of the infrared. I think this is the answer in the large N limit, plus corrections. This is the answer in the large N limit of the pinning field. So it's obviously negative, and it becomes extremely negative at large N. Then there is an answer from the epsilon expansion, which is minus n plus 8 by 16 times epsilon. These are the theory estimates. And I think the higher corrections are known in both cases. What the measurement shows, the measurement on the fuzzy sphere, there is a measurement from the fuzzy sphere. We heard some gong show talk yesterday about the fuzzy sphere, about the paper of Zhu et al. The measurement from the fuzzy sphere, I think, is like minus 0.6, if I remember correctly. It was done by Zhu et al. I might be misremembering this number. It's roughly consistent. And there are various other measurements that are roughly consistent. Another thing is that...
N equals 1, or what is N?
Yeah, this is N equals 1, but you have to maybe go one more order. It would be a little bit...
No, I mean the fuzzy sphere is always for N equals 1, right?
Yeah, the fuzzy sphere is for N equals 1. I don't know if the fuzzy sphere calculation was done for N equals 2 or higher. There are some experts in the audience. I don't remember. And another thing that was calculated is the scaling dimension of the order parameter itself. So we know the order parameter scaling dimension in the bulk. So we know it here. It's well, in 2 dimensions it's 1/8, but in 2 + 1 it's 0.51. But there is a separate operator that sits on the line defect. We have also an the order parameter phi gets renormalized when it's on the line defect. Maybe you can call it phi hat. And that turns out to be 1.5, roughly speaking, both from the epsilon expansion and large N and measurements. And that's basically why the pinning field is generic, because that means that it starts its life as a relevant perturbation with dimension 0.5, roughly, and then it flows to 1.5 in the long distances, which means that it's a stable fixed point. So it's a completely stable fixed point that cannot be perturbed. So that's why it's kind of dangerous to have external magnetic field in the Ising model, because you just inevitably flow to an infrared stable fixed point, and there is no way out. The order parameter becomes too heavy. Yeah.
Sorry, I missed the setup when you talk about the theory. What is N and what is epsilon?
Yeah, I didn't really explain. I just wanted to show you that there are we know some things about this object. So there is a generalization where you, instead of looking at the Ising model, you study the Wilson-Fisher fixed point, and the pinning field is in the direction phi 1. And phi is a vector that has n components, and that's what n is. So there is such a class of pinning fields, and you can do large N expansion for them and epsilon expansion. And so we know that this is a stable fixed point. It's an infrared stable fixed point. There is no relevant perturbation whatsoever. So there is no way to get out of that fixed point if there is such a defect. Yeah. So this was just a quick summary of some facts about the pinning field. And tomorrow I'll talk about the boson Kondo problem, which is a more involved conformal line operator in Wilson-Fisher fixed points. Now, if there are any questions in the last couple of 5 minutes, any questions about any of what I said? Yeah.
Yesterday you said that for non-local operators there is a natural normalization. Using that normalization, can you extract something that is still independent from the linear term in R?
Yeah, so the reason I emphasized this point at least 5 times yesterday was exactly so that people don't ask me how can this exist. If you can just normalize the line, if you could take this line operator and multiply it by square root of 2, that would creep into that, right? It would just shift s by square root of 2, by the logarithm of square root of 2. So the whole reason that I'm now comfortable saying that s makes sense and scheme independent is exactly because the normalization of line operators is universal. So the only divergence is extensive. It's linear in R. There is no divergence that's nonlinear, that's sub-extensive. And because there is no divergence that is sub-extensive, this is a scheme-independent quantity. So this whole discussion is the same as saying that operators which are extended have a universal normalization. You see? That's exactly why I emphasized it yesterday.
And for higher dimensional defects, when there are like, you can write more invariants?
Yes. Then this operator would not be enough. For instance, if you look at 3-dimensional defects in 5-dimensional quantum field theory, there will be a divergence that goes like lambda r to the 5, lambda r, some lambda prime r cubed, plus lambda double prime r. And then maybe there is some finite piece which is scheme independent, but then you'll have to consider a much more complicated differential operator. And then the object that you'll get may or may not be monotonic. Maybe it won't be monotonic. We don't know. Just in this case, it's sufficiently simple that you can, with some work, prove that this is a monotonic function. Quite rigorously. Yeah.
You mentioned there that there was some proof in 2+1 for equal.
Yeah.
But there's a similar problem there.
So for p equals 2, I can say, so the partition functions for p equals 2 are partition functions on spheres embedded, let's say, in R3. And the structure of the divergences is a quadratic divergence, but then there is a logarithmic piece. And this actually is already universal. It cannot be removed by a counter term. And the discussion in that case is about the R dependence of the logarithm. And that's a function that could be monotonic, we don't know. But we know that the infrared value is smaller than the UV value. But we don't, maybe it's monotonic, but we don't know, probably not. Okay? So there you get rid of this by some procedure. Okay. Yes?
Can you bootstrap this thing? Can you bootstrap this?
Can you bootstrap S?
Yeah.
Or maybe the fixed point value. Yeah, you can probably. Dalimil Mazach, who is in Saclay now, I think, has tried.
What's it?
I think Dalimil has tried. Maybe even Wang tried.
But what's the observable your bounding which is related to this? Can't bootstrap partition.
Yes, that is correct.
I think you can with different.
So for in 1+1 dimensions.
With
So
descending operator, you can.
I'll say the answer, at least what has been done. Maybe you can do better than that in the future. But so there is no way to bootstrap it in 2+1 because of what Shai said. We don't know how to bootstrap G in 2+1 or S. We don't know how to bootstrap S in 2+1. In 1+1, there is a trick, which is that it turns out that you don't need to calculate the partition functions of circles in R2. There is an equivalent computation. There is an equivalent computation where you take a torus. So you take a torus and you wrap it around one of the cycles of the torus. And only in 1+1 dimensions, this and these computations are the same. It's a highly non-trivial fact, but it's true. And because these computations are essentially the same, you can use the modular bootstrap. just properties of the modular partition function, of the partition function of tori, to learn something about S in 1 plus 1, but not in 2 plus 1, as far as I know. Okay?
In 2 plus 1 for the P plus 2 case, is it known if you get interesting quantities by looking at different surfaces?
Second, I didn't understand. P what?
For the P equals 2 case, in P equals 2 plus 1.
Oh, this one?
Yeah, in this case.
Yes.
Is it known if you get interesting quantities if you don't look at defects localized on spheres but on some other surface?
Yeah, so if you compute partition functions on some other surface, maybe a torus or something, or some maybe ellipse, we don't know if it's useful. We know very little. We just know a few things that work, and that's it. Yeah.
Is this G determined by the CFT data in the IR, or is it an additional number that has to be supplied for each CFT?
I don't know the answer to that question. I also don't know the answer to that question. Yeah. First of all, a given CFT can have multiple line defects which are conformal. Each comes with its own G. So if you fix the bulk CFT, there is like a collection of line operators which are conformal. Every one of them preserves SL2R, and you can even do a direct sum, you can do a direct sum, you can do fusion. So there is a collection. Is this collection infinite? I don't know.
Is it determined by the G on one of those operators?
Each one of them has its own
G.
G. Each one of them has its own G.
But is it determined by the DCFT data for that line operator, Li?
Okay, let me just get one by one. You're asking a very difficult question. So first of all, we don't know if the space of conformal line operators is even infinite or finite. I don't know the answer to that. In the Ising 3D model, we know a few conformal lines. Maybe there is an infinite number. We don't know. In Maxwell theory, there is certainly an infinite amount, because we can just take Wilson lines of arbitrary charge. Now, you are asking, does the conformals data, so to speak, the scaling dimensions of various defect operators and their OP, does that determine G? I don't know. Sorry to disappoint, I just don't know. It's not known. I believe the answer is no. I believe the answer is no. And the reason I believe the answer is no. But I'm not sure. I believe it's some kind of more intricate data where you need to put it on a circle to see something. Yeah.
Well, at the very least, there'll probably be an ambiguity if you fuse it upward with defect.
Yeah, but that actually affects the DCFT data a little bit. Because if you do 1 plus 1, this defect has 2 unit operators. So there is a multiplicity of unit operators, and that's why G is log 2. So it might be buried in the DCFT data. Nobody has devised an algorithm to extract it from the DCFT data. We just don't know. Any last questions? Yeah.
So you said when you start with one trivial defect, but it has to flow to something conformal. But what if you take this 1 plus 1 plus 1? Can you generate topological defects out of that sometimes?
You want to take direct sums of the binning field?
Right, or of something, right? So you get an argument. So you get an argument why when you start with a trivial defect, it has to flow.
Yeah, you want to start with that.
And now
in the ultraviolet, couple it to the bulk and generate a topological line.
Ah.
Yeah, I'm very certain that that's possible. Yeah. In fact, I can give you simple examples afterwards. Yeah, it's very easy. Okay. Yeah, one more.
You mentioned that the physical interpretation of the entropy is whether the impurity pulls in degrees of freedom from the bulk or it pushes them away. It seems intuitive that at most you can push away whatever was there at the beginning.
Yes.
So it should be bounded by minus the central charge of the bulk or something.
Yeah, so you could make a conjecture that maybe the GIs, let's look at the log, let's look at the SIs, because I used SI. GI is like an exponent of S. I sometimes use G, which is exponent of S. It's just a notation that I sometimes use. So you can ask, is the SIs boundable from below? Maybe it cannot be smaller than some negative number.
Like the central charge of the bulk.
Yeah, maybe it's the central charge of the bulk critical point, maybe the F coefficient. That would be lovely.
But
We don't even know if that's true in 1 + 1 dimensions. But if you look at the bootstrap that I referred to when I maybe responded to Shai, they try to do exactly that in 1 + 1 dimensions, and for some small values of central charge, they were able to. So we have some hints in 1 + 1 that maybe such an inequality exists. Yeah.
If there are no more questions, thank you very much.